All right, so today we're going to look at matrix equations. Now, matrix equations are very closely linked to the vector equations that we dealt with in the last section. In fact, if you remember the last section, at the very end, we were asking ourselves, is B in the span of the vectors that make up the columns of some matrix? So whenever we deal with matrix equations, we have to define how we want to multiply a matrix times a vector. Okay, so a matrix is going to multiply a vector. Now I've tried to illustrate that here. Um, Pretend that we have some sort of a matrix and it's V1, V2, all the way through Vn are the columns of our matrix. Okay, so this V1 stands for a column vector and V2 stands for a different column vector. And so these VI's are the columns of our matrix. If we're going to multiply that times a vector, and which I called x1, x2, all the way down to xn, then what that is really doing is it's taking this first column of our matrix and multiplying it times this entry here of x1. So it's a scalar times a vector, and then we're going to do the same thing with vector v2, scalar times the vector, and we keep doing that until we get down to our last vector times our last scalar. Okay? Once we've multiplied scalar times vector, scalar times vector, scalar times vector, then we're going to add up all of those things, and that is how we multiply a matrix times a vector. Now, one of the things you'll notice really quickly here is that the number of columns in my matrix has to add up. So the number of columns in this first matrix has to be the exact same as the number of entries in your vector. Okay, we say the columns in this first matrix, if there are n of them, there's going to have to be n rows in our vector. So those things do have to match up in order for us to be able to multiply. So we do have to match up some sizes, but as long as we have n columns and n rows in our vector, then we're good to go. So let's actually take and compute the following matrix times vector. So we have the matrix you can see here is 4, negative 2, 5, 0, 6, negative 1, and the vector is 2, 3, negative 2. All right? That is in the Word document. Okay, so what we're going to do is we are going to take this scalar 2 and multiply it times the vector 4, 0. So we take 2 times, I should have done this beforehand, but that's okay. 2 times the vector 4, 0. If you want to do this in math, you can, or excuse me, in Microsoft Word, you can do it. Plus 3 times the vector 2, negative 2, 6. Takes longer to type out than it does to write. So negative 2, 6. And then plus negative 2. Oops. We'll call that minus 2 multiplied times the vector 5, negative 1. Okay, and whatever the resulting vector is, that is our result of taking the matrix multiplied times this vector. Okay, now I'm going to copy and paste. I'll finish this out just so we can show you how that's done, but we've done this before. We've done scalar multiplication times vectors. That first 2 times 4, 0, it's going to become the vector 8, 0. 3 times negative 2 is negative 6. 3 times 6 is 18. Negative 2 times 5 is a minus 10. You know what I'm going to do? I'm going to do a plus in front. Oops. And then negative 2 times negative 1 is going to be a positive 2. And so the final vector that we're looking at, excuse me, 8 plus negative 6 plus negative 10, that should give me a negative 8 as my first entry. 0 plus 18 plus 2 gives me a 20 as my second entry. So when you take a matrix times a vector, notice the ending result is in fact another vector. Now, interestingly enough, the vector that you started with was a three-dimensional vector. It came from R3, okay? And that was because we had to have three scalars because we ended up with because we started with three columns in our matrix. But our end result was a two-dimensional vector. And that came from the fact that there were two rows in our matrix. So this matrix tells you what size vector you're going to have to multiply by, and also what size vector you're going to get out. You're going to multiply by a three-dimensional vector because we have to have three columns, and you get out a two-dimensional vector because you have two rows. So here's what I'd like you to do. I'd like you to try multiplying the following matrix times the following vector. 1, negative 10, 3, 8, negative 1, 7 as your matrix, and 2, 4 as your vector. So go ahead and push pause and then do that. All right, so what we do is we take this column and we treat that as a vector, multiply it by the number 2, take this column, treat it as a vector, multiply it by the number 4, and then add up that result. So let's go ahead and do that. I'm going to do that on the Word document here. So we're going to take 2, multiply by 1, 3, negative 1, and then take 4 and multiply that times negative 10, 8, 7. And when you go ahead and do that, we're going to get some vector. In fact, you could probably do it all in one step here if we like. I'm going to do that. 2 times 1 plus 4 times negative 10 is a negative 38. 2 times 3 plus 4 times 8. Just punch that into your calculator if you're 2 times 3 plus 4 times 8 is positive 38. And then 2 times negative 1 plus 4 times 7 is a 26. So when you multiply this matrix times this vector, you get out the vector negative 38, 38, 26. Okay, so that's what matrix multiplication does. Now, what we're going to do is we're going to take matrix multiplication, now that we know how to do it, and create a matrix equation. So we're going to let A be the matrix with columns V1 through Vn. So it's the exact same matrix we've been using. So the columns are going to be vectors. We say that the matrix equation is the equation AX equals B, where A is the matrix, X is some vector, and B is some other vector. Notice again, X and B will have to have the right dimensions for this to work. Since A has n columns, X is going to have that many entries. And then B will be however many rows A has. That'll be the size of B. Now, notice that when we wrote this out, on the Word document, it actually, we wrote it out as a vector equation. So since we know that column 1 is going to have to multiply times entry 1 of x, we get x1 times v1 plus x2 times v2 plus so on and so forth, xn times vn equals b. And therefore the matrix equation and the vector equation here are the exact same thing. Therefore, I shouldn't say the exact same thing. They are going to give us the exact same solutions. All right, so they're going to give us the same set of solutions. All right, they are written differently. We're utilizing multiplication in different purposes, but to do the matrix equation, it's going to have an equivalent solution set to the vector equation. Because they're the same exact solution set, it's going to be useful to basically go back and forth between those two notations, and also we can go back, if we wanted to the systems of linear equations notations as well. All right, so they're going to give us the same solution set, and that gives us a freedom of sort of moving back and forth between different different notations. So what I'd like you to do is hit pause on the video. We did this one earlier. We did something very similar. We did this one, I believe, exactly. We came out with, you multiply this matrix times this vector, and you get out that vector. I want you to go ahead and write that. This is a matrix equation. Write it as a vector equation. So write out vector 1 times a constant plus vector 2 times a constant equals that final vector. Push pause on the video, take a couple of seconds to do that. All right. So hopefully you went ahead and did that. Now again, we did this one by hand earlier, so we found that when you multiply this matrix times this vector, you do in fact end up with negative 820. And the way we multiplied matrix times vector was by just taking, let me scroll these down, was by taking 2 times the vector 4, 0, plus 3 times the vector negative 2, 6, minus 2 times the vector 5, negative 1. Notice that's already the long form vector expansion of the matrix times this vector 2, 3, negative 2. And so to convert it, into a vector equation, well, all we have to do is write that is equal to negative 820. Okay, so that's our vector equation. Matrix equation, vector equation, and they're telling us essentially the exact same information. Okay, just one in a matrix format, the other in a vector format. Now, one thing I will say right now about the vector equation, remember as always, I multiplied the left by, I put the 2 on the left-hand side. Some people like to put the 2 on the right-hand side. Again, 3, you could put that on the left or the right-hand side. Whichever side you put that scalar on is a little bit arbitrary. Just as long as you've matched up the right scalars with the right vectors. Okay, so this top scalar matches up with the 4, 0. 3 matches up with negative 6, negative 2, 6, and then negative 2 matches up with 5, negative 1. So let's do one more of those, but in the reverse situation. We're going to take a vector equation and write it as a matrix equation. You can do the calculations and see that this one is true, but I want you to write this as matrix times a vector equals another vector. Okay, push pause on the video. So hopefully you went ahead and did that. Again, if you haven't done that, do it. Push pause and go ahead and do that. But for right now, we're going to uh, do the computations here. So notice that here we have column vectors 1, 4, and 5, negative 2. So that those column vectors are going to comprise the first and second column of my matrix. The vector that I'm multiplying by, well, it has to, since we have two columns, it has to be two-dimensional. And therefore, we're just going to be two-dimensional. I've multiplied 3 times this first column, and I've multiplied a negative 6 times that second column. And therefore, my answer equaling negative 27, 24, that's not going to change and no matter what I put in there. So there we go. So that is the way you'd write matrix times vector equals a resulting vector. Okay, so matrix times a vector is a vector. Now, we saw that the matrix equation AX equals B is going to have the same solution set as the vector equation. Now we can go back and forth from that. Notice that the matrix equation having the same solution set as the vector equation, that vector equation is just a linear combination. So what the vector equation is saying B is equal to a linear combination of the vectors v1 through vn. And so we can take all the stuff we learned in section 1.3 and we can ask similar questions. We can say, is B a linear combination of the columns of A? Well, that's equivalent to solving the matrix equation and is equivalent to solving the vector equation. Or we can say, is B in the span of the column of A? The columns, of A. Is B in the span? Is B a linear combination of the columns of A? It's kind of the same type of question. We're asking, does there exist this vector x, which I can multiply? Do these vectors, do these values for x exist? So we can solve a matrix equation for a vector x. Now, because we know that the matrix equation is going to have the same solution set as the vector equation, and we saw last time that the way to solve the vector equation is to create an augmented matrix and we'll reduce that augmented matrix. Well, if you're ever trying to solve a matrix equation, AX equals B for X, the way to do that is to create an augmented matrix and then row reduce it. That's what we're going to do. So now the one thing you have to understand about this is what's that augmented matrix going to look like? Well, it's going to look like the coefficients of our x values are coming from these vectors, and this b is the constant vector when you write it as a vector equation. So basically what I'm trying to get at is that the augmented matrix is simply going to be a 2 by 3 matrix where the first block looks exactly like A, the first 2 by 2 piece, and then the last column is the column of my constants. So if I put that in row reduced echelon form, and how am I going to do this? Well, I'm going to do it with the matrix, or I guess you could do it by hand if you'd like to, but I'm just going to take, like we always do, and go into my matrix menu, edit some matrix. I guess I'll call it A, although it's not the exact same A that we've been dealing with. So matrix A, it's going to be a 2x3 matrix, and then we put in the entries of that matrix. All right. So just as a reminder, that was 2. Whoops, thought I was on that. Excuse me, 2, -3, 4, and then 5, 4, -7. Okay, we're going to quit that, go back to the matrix menu. Hopefully I did that right. We're going to row reduce echelon form that. Row reduce echelon form. Matrix A. Again, I'm kind of not perfectly using that notation. I've kind of used A for 2 different matrices. One was the A in the actual problem, and the other was the augmented matrix. So I'm being a little bit sloppy with that. You could probably use a different letter if you want, but I think we can all figure that out. And when we reduce that, this is what we end up with. Okay? So 1, 0, -5/23, 0, 1, -34/23. Now, if we go back to what we were actually asking, solve the matrix equation for x, what we just found out is that in order for ax equal b to be true, x needed to be the vector. I should probably put this in bold. X needed to be the vector -5/23 and -34/23. Okay, so in order for that to be true, what we were getting, again, when we row reduced echelon form that, we ended up with the equation x1 had to be -5/23 and x2 had to be -34/23. Okay, which basically is just telling you your entries of the vector you would have needed for ax equals b to be true. All right, hopefully that all makes sense. You row reduce it, you figure out that x1 had to be -5/23, x2 had to be -34/23. Therefore, in order to get this equation to be true, your x value, your x vector had to be -5/23 and -34/23. Now, what I would like you to do on your own is do the exact same thing for this b. All right, so take 2, -3, 5, 4 as your a, take b as -350, and I want you to create the augmented matrix and use row reducing of the augmented matrix to be able to solve that. Okay, push pause on the video. All right, hopefully you went ahead and did that. What I am going to do is I'm going to go back to my calculator. Now, I want to sort of skip a couple of steps here because we've done this a number of times, but what we're going to do is go edit one of our matrices. Matrix A is the easy one to edit because we've already dealt with it, and it already has this right 2 by 2 starting block in it. In other words, the 2, -3, 5, 4 of our original matrix did not change. What did change is the B value. The B was -3 and 50. All right, so we go back to the home screen. I'm going to hit second enter a couple of times because that'll just give me back row reduced echelon form, my augmented matrix, and I end up with this. And basically what that's telling me is that x1 has to be 6 and x2 has to be 5. Okay, so again, this column stood for the coefficients of x1, this column stood for the coefficients of x2, and therefore, if I'm doing another problem, if I'm doing the problem we just said, then my solution will be that the vector x that I needed to multiply was in fact the vector with leading entry of 6 and second entry of 5. All right, so my solution would be that in order for ax equals b to be true, the vector x would have had to have been 6, 5. Now, another way to write is b is solve the matrix equation for b is to say is b in the span of the columns of A, okay? Notice that is b in the span of the columns of A is equivalent to solving the matrix equation AX equals B. So I want you to see is B in the span of the columns of A, and then if it is, write down the vector X that would generate AX equals B. Another way to write that is to say write down the weights of the columns, right? Because column 1 is going to be multiplied by x1, column 2 by x2, column 3 by x3. So go ahead and push pause on the video and solve that. Right, so here's how we accomplish that goal. Here's how we see if B is in the span of the columns of A. Or again, in other words, is B a linear combination of the columns of A? So first off, we create an augmented matrix. Create the augmented matrix where our first column, second column, and third column are all the columns of A. And then our last column, that constant column, is the columns of B. Now this is associated with the vector equation. This is also associated with a system of linear equations. So we row reduce it. We put the matrix, this augmented matrix, in row reduced echelon form. Again, that's a button on our calculator so that we can save a lot of time. And when we put that in row reduced echelon form, what I got, hopefully I didn't make a mistake, was this matrix here. 1, 0, -1.5, 0. 0, 1, -0.75, 0. And then 0, 0, 0, 1. Now, if you recall our row reduced echelon form stuff, that 0, 0, 0, 1 at the end means 0 equals 1, and so that is the situation which we know gives us no solution. Okay, so that row of zeros and then a 1 means that there's no solution. Now think about what that means in the context of this problem. Is B in the span? We can say no, it is not in the span because there's no solution to the equation AX equals B. So since there's no solution to that equation, B cannot be in the span, and B is not in the span of the columns of A. I want you to try the same thing, but for this other vector B. Okay, this other vector B now is the vector B, which is equal to 6, 8, 4. And if it is, let's write the weights of the vectors, write those coefficients. Push pause on the video. All right, so hopefully you went ahead and did that. And so if you did go ahead and do that, again, always push pause if you haven't. So the concept is the exact same. We start out with A and B. Now our B is changed to 684. We create the augmented matrix that has the first 3 columns as our matrix A and the 4th column as our matrix B, or as our vector B, I should say. Although a vector is a type of a matrix. So we have this column B. Now, when you row reduce echelon form that, you end up with 1, 0, negative 1.52, 0, 1, negative 0.752, and then a row of zeros. Now, this is the infinitely many solutions case. So what this is really telling us is that x1 minus 1.5 x3 has to be equal to 2, and telling us that x2 minus 0.75 times x3 is also equal to 2. And then the general solution, we would say x3 is a free variable. Okay, so I have 2 pivot columns here. We can see 2 pivot columns, one for x1, one for x2, and then this third column is not a pivot, and therefore it's representing some sort of a free variable. Now we can rewrite this if we want to. Instead of doing a subtract 1.5 x3 on the left-hand side of the equation, we can add 1.5 x3 to both sides. I'm just going to do that simply by changing up where my equal is. Again, if you add 1.5 x3 to both sides, that's what you get. Similarly, if you add 0.75 x3 to both sides, what you end up with is that. Now, again, what this means is that there were infinitely many ways, there were infinitely many vectors that we could have multiplied by A and had them given us out B. So there's infinitely many of those, but they all have this pattern. Okay. Now, again, sometimes you want to use something, but sometimes you want to use a specific value for x3, but quite frankly, you can use any value for x3 you want if you're just looking for a single vector that has the appropriate weights to end up with the vector B. Okay, so if I would have plugged in 0 to x3, I would have ended up with the vector 220. And that would have been a fine answer for that problem, that the vector 220, when you multiply it times A, gives you out vector B. You could have also, by the way, used another number. Let's say I used the number 2 in for x3. If I put in 2 for x3 equals 2, then my x2 would have been 0.75 times 2 plus 2. And I would have ended up with a 3.5 in for my second entry. Okay, that equation, when I plug in 2 for x3, gives me that. Similarly, if you were to plug in 2 for x3, what would have happened to the first equation? Well, 1.5 times 2 plus 2, that gives me out a 5. So this would alternatively have been an answer. And both of these would have been correct answers. You can multiply 2, 2, 0 by matrix A and end up getting out your B. You can also multiply 5, 3.52 by your A and get out the exact same answer. All right. In fact, let's do one more. You could have multiplied by another matrix. Now this is kind of, as you can see, I'm just picking different numbers for your free variable. You can pick any number that you want. Maybe I want to pick negative 20 for my free variable. Once you've plugged in negative 20 into your free variable, you'd have to plug it in into this equation to get your second variable, and you'd have to plug it into this equation to get your first variable. So let me start with the second equation. 0.75 times negative 20 plus 2 gives me a negative 13. And then 1.5 times negative 20 plus 2 would have given me a negative 28. So again, all three of these vectors would have given me the exact same b if you multiply times a. So a times this x would have given me b, a times this x would have given me b, a times this x would have given me b. In fact, there's infinitely many different x's you can choose based on just picking your numerical value for your x3 that you want. All right. So there you go. There's the weights of the vectors. Again, I'm being a little bit loose. The weights of the vectors are the entries of vector x. Okay. Now we have one more really big type of problem in this chapter, and it's the problem that involves spanning Rn. Okay. Now we saw earlier Rn is basically the set of all column vectors within entries. So it's basically real numbered column vectors within entries. So instead of asking, will the, if a, let me put it this way, instead of asking if a single vector is in the span of the columns of A, we're going to ask, is every vector in Rn in the span of the columns of A? All right. So not is B, but is every B in the span of the columns of A. Okay. And when it's true that every single B that you could dream of is a linear combination of the columns of A, then that's when we say the columns of A span Rn. Okay, so that means that you can make, if I give you a vector B, you can find at least one solution, no matter which B I give you. So here's what we do. We say, do the columns of A span R2? In other words, if we were looking for a vector b, would there be any b's that we couldn't find a linear combination for? All right, let's think through this problem. How would I approach this for a general b? Okay, well, let's go through what we would do if I was given a matrix A and a vector B, which we're going to call in general having entries B1 and B2. Whoops. So we're going to say no matter what values this vector takes, can we find a solution? I shouldn't have done that. Okay. And remember, we're trying to find a solution to this matrix equation. Can we find an x which works for that matrix equation? Now, what we would have done before is we would have created an augmented matrix. We specifically would have created an augmented matrix with 2 rows and 3 columns. And then we would have row reduced it. 2, -3, and then B1. Just a second, I'll unbold those. 5, 4, B2. All right. So that would have been our augmented matrix. And then we would have went and row reduced this. Now, I want you to remember what row reduction does. We multiply by a constant on one row. We can swap rows. We can take a multiple of this row plus a multiple of this row and then replace. Or multiply this row plus a multiple of this row and replace the second. Notice what that would do to these B2s and B1 entries. Basically, we're just going to get linear combinations of B1s and B2s on our right-hand side. We're never going to multiply by 0, so we'll always have some sort of a B1 and a B2 existing in one or both of these slots. So amongst our linear combinations that are going to end up here when we row reduce, what we know is that that last entry, whatever it happens to be, is going to be some linear combination. We'll call it A1 times B1 plus A2 times B2. It's going to look something like that, and it's going to look like something like this. Now, these coefficients might be nasty, but we know that they're not both going to be 0. All right, when you have a linear combination, because of the way row reduction works, we know we're going to end up with linear combinations over here. Now, how is this thing going to row reduce? Well, this thing is going to row reduce exactly like 2, -3, 5, 4 is going to row reduce. Okay? So go ahead and row reduce 2, -3, 5, 4. Okay, without the b's. Again, pretend the b's don't exist. Just row reduce the matrix A, essentially. So I'm row reducing the matrix A. What you'll find, if you push pause, you can do that by yourself. Otherwise, you can just figure out that it's going to be 1, 0, 0, 1. When you row reduce A, you get 1, 0, 0, 1. And then row reducing this last column is just giving you linear combinations of stuff with b's in it. Now notice, no matter what linear combination this is of stuff with b's in it, x1 is going to be equal to that number. And therefore there is going to be a solution there. And x2 is going to be equal to that number. So there is going to be a solution there. Okay? Now imagine for a moment it didn't end up this way. Imagine for a moment that when you row reduced A, you wound up with a double zero in this last row. Well, because we're looking for this for any B's, because of this double zero in this last row, there is going to be a way to get a no solution scenario. There is going to be a way to get 0, 0, 1. We just have to choose the right values of B's, and we'd get that. And therefore, in order to for this AX equals B to always have a solution, basically when I row reduce echelon form A, I need pivot points in each row. Okay, I need row 1 to have a pivot point, I need row 2. I can never be at this place where I have zeros all and then a final thing on the end. And so when we actually do this, we're going to forget about this third column. When we actually go ahead and do this, all we're going to do is say, well, here was A. When I put A into row reduced echelon form, I ended up with a really nice matrix. That matrix had 2 pivot points. I needed that many pivot points. So I had 2 pivot points, 2 pivot columns, and I had that many rows, and therefore the matrix equation AX equals B is going to have a solution for all B. All right? So AX equals B. Does have a solution for every vector B. And that's because we have enough pivot points. In this case, we needed 2, we got 2. Okay, the pivot points need to cover every single row. Okay. And therefore, we can say that the matrix A spans R2. All right. I forgot it. My R. Hopefully that all makes sense. That's supposed to be a vector B. Okay. So the matrix equation has a solution for every B. That's because we had enough pivot points. We had 1 pivot point for every single row. And therefore, since AX equals B always has a solution, the matrix A spans R2. Anyway, you can get any vector from R2 as what we call an image of the matrix A. We'll figure out that language a little bit later. All right, hopefully that all makes sense. So what I'd like you to do is asked this. Do the columns of A span R3? And again, we can restate that. Sometimes we say, does A span R3? Do the columns of A span R3? Go push pause on the video and see what happens. All right, so let's take this a question and say, do the columns of A span R3? Oops, do the columns of A span R3? I was on the wrong slide there for a second. 1, 2, -3, 0, 4, -3, 2, 0, -3. So again, what we're going to do is we're going to think that there's this weird column of B that we can row reduce. And that column of B that we can row reduce can end up as anything we want it to be. All right. So what we do is we just take our matrix A. Again, this is like the coefficient matrix. This is not the augmented. Again, we'd have another column if we wanted an augmented matrix here. So we take this matrix A, and we pretend that there's a column there. We row reduce it. And in this case, I got a third row. This is the important one that says 0, 0, 0. And then again, we would have this augmented matrix, but but we're missing this last column. But that last column, remember, I can make basically anything I want. So I could make this last column 0, 0, 1. And therefore, there are going to be situations in which you're going to end up with a last row, which is 0, 0, 0, 1, when you have an augmented matrix there. Okay? So there are going to be, let me write this down, there are going to be some B vectors, again, the B ones, which yield a no solution scenario, which you're going to end up with, again, 1 right here when you row reduce it. And therefore, the columns of A are not, in fact, spanning R3. Because there's B's in R3 that would not work, because there are some no solution scenarios, the columns don't span R3. All right, in that situation. For this matrix A, the columns don't span. I want you to do one more of those. Go ahead and do the next example. And this matrix is not a square matrix. This matrix is going to be a 3 by 4 matrix. So what that means is we're going to have 4 variables, and we're going to ask ourselves, do the columns of A span R3? Do the columns of A is there some linear combination that will give us B no matter what B we choose? Go ahead and do that using that row reduced echelon form technique we showed. Push pause on the video. All right, so hopefully you went ahead and did that. We're going to go to what the technique would be. First, we take our matrix A, and again, we're imagining this as the first chunk of an augmented matrix that's going to have a column here to the right. When you put that A into row reduced echelon form, you get this. You get 3 pivot positions, and then you get a free variable here, and then you're going to have, again, we're going to think that we could put any sort of B over here towards the right if we had a augmented matrix. Now, no matter what values we choose for B, no matter what value I put here, here, and here, you're always going to be able to find a solution. Okay? The existence of a free variable doesn't mean that you can't find a solution. In fact, it means that no matter what value of B I choose, there's going to be like infinitely many solutions. Okay, so no matter what values I have here, I will be able to find a solution because I have a pivot point for each of my rows. All right, so it's okay to have that free variable in there. This just means that no matter what B I choose, there are going to be infinitely many solutions. All right, so since there are 3 pivot points, a pivot point for each row, there is no way to get ourselves in a no solution scenario. Again, remember the no solution scenario is all zeros, and then in the augmented part there'd be something. So there's no way to get that no solution scenario, and therefore, actually let me just pull this up. Therefore, the columns of A do in fact span R3. No matter what B you give me, I can write that B as a linear combination of the columns of A. So in fact, in this situation, columns of A do span R3. Now, one little tidbit that I want you to take into account. Let's clear out my calculator. What if I asked you, do the columns of A span R3, and let's let my columns of A be, well, we'll let the two columns of A, my first column will be 1, 1, 1. My second column will be -2, 4, 7. Now I can already tell you that these columns are not going to span R3. And why is that? Well, at most, because we have two columns here, the most number of pivot positions we can get is 2. All right? So in the best case scenario, when we row reduce this, we end up with 2 pivot positions. That's not enough. We need 3. Okay? So it's pretty clear that in order to span R3, you need to have at least 3 columns. And the same thing is true with R4. In order to span R4, you need at least 4 columns, and so on and so forth. Okay? In fact, if you went and you tried to row reduce echelon form that matrix, some calculators, I don't know if this one does or not, but some calculators will in fact give you an error. Yep, because there's an invalid dimension. All right. By the way, if you ever want to avoid that error, what you can do is you can kind of hack the calculator by adding an additional column of all zeros. Okay, so if you ever want your calculator to row reduce something and it has more columns than rows, then you can just add in a column of zeros, and then when you go back and you row reduce, then you can see, oh yeah, we only can get 2 pivot positions. And again, pretend that row of zeros doesn't exist, but this last, excuse me, pretend that column of zeros doesn't exist. This last row of zeros would give me the no solution case, 0, 0, and then the augmented part, we could put a 1 right there. Okay? So a little bit of trick to the calculator, but again, if you only have 2 vectors and you're asking, does it span R3, you don't have enough vectors. Okay? Or if you're asking if there are 4 vectors and you ask, does this span R7? Well, of course not, because we don't have enough vectors. Hopefully that makes sense, that little aside. Now, the last thing I wanted to talk about in this section is just some logically equivalent statements. All right, we've done a lot of different definitions, so we understand that there's a lot of different definitions. I've been trying to make some connections, like talking about span and talking about linear combinations in the same breath, but I wanted to make it a little bit formal. And we're going to start getting into this because there's going to be a lot of true false questions. There's going to be a lot of other stuff that's in the homework that is going to require you to think logically. So let's pretend A is an M by N matrix, M rows, N columns. Then the following statements are either all true or they're all false. Okay? So if one of them's true, they're all true. Or if one of them's false, they're all false. And it's because they're all equivalent to each other. So these statements are all equivalent to each other, meaning that if this is true, then the others are true. If this is false, then the others are false. So let's read this. For each B in Rm, the equation has a solution. Okay, so this equation has a solution for every B. Each B in Rm is a linear combination of the columns of A. Well, again, the connection between the matrix equation and the vector equation, that vector equation means that this written in vector form means that linear combination of the columns of A gives you B, right? So these two are equivalent, meaning they're really saying the same thing. The columns of A span Rm. Again, that's what we've been using. And then A has a pivot position in every row. A having a pivot position meant that they span Rm, means that every B is a linear combination of the columns of A, means that for each B, that matrix equation has a solution. So all of these are equivalent. All of these are essentially what we've been using to solve the question, do the columns of A span Rm? All right, we did that in the previous few examples. And so now we just sort of codified that using logically equivalent statements. So that is it for section 1.4. That's what we're going to stop at. If these concepts don't make sense, make sure you reach out to me and get help. Other than that, we'll start back in section 1.5.